Titration is a technique used to determine the concentration of an unknown solution. And in order to be able to do that, we need to know the concentration of one of the solutions. So in the following problem, we are taking advantage of a neutralization reaction between an acid and a base. And we know the concentration of the base, so we can use that to figure out the concentration of the acid solution. So the problem states, what is the molarity? And of course, this is a type of concentration that is abbreviated as a capital M. Of a sulfuric acid solution, if 15 milliliters of a 0.182 molar sodium hydroxide solution is needed to neutralize a 20 milliliter sample of sulfuric acid. So the very first thing that we need to do here is remember what molarity means. So molarity is expressed as moles of solute divided by liters of solution. And the specific units here are really important. Notice that we need to have the volume expressed in liters of solution specifically. So if we wanted to calculate the molarity of the sulfuric acid solution, well, we would need to plug in the moles of solute. And if we look at the problem, really what we need to be able to do that is the moles of sulfuric acid. But in the problem, the moles of sulfuric acid are not given to us anywhere. So we will need to figure that out before we can solve that problem. The next thing we need is the volume of solution. And notice that that information is provided to us. So it tells us that we have 20 milliliters of solution. There is one issue here, and that is that in order to calculate molarity, we need that to be in liters of solution. And right now it's expressed in milliliters. But that's not too bad. That's a simple unit conversion that we can do. So we can take our 20 milliliters of solution and we'll convert that to liters. And since here milliliters are in the numerator, we need to put milliliters in the denominator to cancel that out. And in 1 liter of solution, we have 1,000 milliliters. So now the milliliters cancel out and we can express that volume as liters of solution. And I'm just being careful here to keep 3 significant figures because there are 3 significant figures in the problem. So that gets plugged in here. We know the liters of solution. That is good to go. The problem is that we don't know the moles of sulfuric acid, and that's what we have to figure out. So the very first thing that we're going to do here is we know the concentration of the sodium hydroxide solution, and we know the volume of sodium hydroxide solution. Based on that information, we can calculate the moles of sodium hydroxide. And titration, the entire premise of titration rests on the fact that in order to neutralize each other, the number of moles of acid have to equal the number of moles of base. So if we can figure out the moles of hydroxide in solution, well, the moles of the acid have to be equal to that. So by figuring out the concentration of the number of moles of the base, we will figure out the moles of sulfuric acid, which we can then plug into our concentration expression and figure out molarity. So the first thing we're going to do before we do any of that is write a balanced chemical equation. So I'm going to take the acid and react it with the base in a neutralization reaction. Okay, we can kind of treat this like a double replacement reaction. So what I'm going to do is break apart each compound into the ions that it comes from. Notice that this looks a lot like sulfate. So that comes from a sulfate anion and a hydrogen ion. And then I'm going to do the same thing to sodium and hydroxide. If we break that apart, we get a sodium ion and a hydroxide anion. When we do a neutralization reaction, one of the products is always going to be water and the other product is going to be some sort of salt. And salt really means ionic compound. So we have to generate a water molecule. And in order for that to happen, well, the only way I can generate water is to find an OH and give it a hydrogen. So the hydrogen and the hydroxide are going to combine to generate a water molecule. That's where that comes from. The remaining ions are going to generate an ionic compound that we call a salt. So here we have a sodium, we have a sulfate. We're going to combine those to generate a new compound. Now, here the charges don't cancel out because we have a +1 and a -2. So in order to generate a new formula, we have to cross those charges. So we'll write our cation first, then our anion second, and then this charge gets brought down. Now, of course, we could bring the 1 down here, but when the subscript is 1, we don't bother to indicate that. So our new formula is Na2SO4. And I'm going to rewrite this in a nice, neater chemical equation. Okay, now that we have that, we have to make sure that this equation is balanced. And right now it isn't. We have 2 sodiums on the right and only 1 on the left. Keep in mind that when you have a situation where you have water on one side of the equation and hydroxide on the other side of the equation, it can be helpful to rewrite water as HOH so that you can kind of treat it like a polyatomic ion. It really isn't, but it just simplifies things and makes it easier to balance. So on the right, we have 2 sodiums. On the left, we have 1. So I will multiply that by 2. That takes care of the sodium. Now notice on the right side of the equation, we have 1 hydroxide, and here now we have 2. So I have to multiply this by 2, which really means the water gets multiplied by 2. Now we have 2 hydrogens on the right and 2 on the left, so that looks like it's good to go. And then we have 1 sulfate on the right and 1 sulfate on the left. So that is balanced and good to go. I will take that equation and move it to the next page. Okay, so there's our equation, and I'll just bring the problem around as well so I can reference the information that we have there. Okay, so there's our problem. There is our balanced chemical equation. Okay, and what we're really trying to figure out right now is the moles of H2SO4. That is our unknown. However, the information that is given to us, what we do know here is that we have 15 milliliters of sodium hydroxide solution, and that solution has a concentration of 0.182 molarity. Here it's important to recognize what molarity means. And what this concentration is really saying is that if we were to have 1 liter of that sodium hydroxide solution, it would contain 0.182 moles of sodium hydroxide. As soon as we have that, we can use this fact as a conversion factor, because now we have the volume of sodium hydroxide, we have a conversion factor that can convert it into moles of sodium hydroxide, and that way we can get to moles of sodium hydroxide. So let's start with that. I'm always start the calculations with a number that is off by itself and not part of a conversion factor. So I will start off with 15 milliliters of the sodium hydroxide solution. And then I can use this conversion factor to get to moles. There is one problem here, and that is the fact that the unit right now is expressed in milliliters, but the conversion factor is expressed in liters. So I do need to get those units to match, and I'm going to convert the milliliters to liters first. So in 1,000 milliliters of solution, we have 1 liter of solution. And now our milliliters cancel out, and we have liters of solution. Now, in order to get to moles of sodium hydroxide, I can use this conversion factor. So in 1 liter of solution, we have 0.182 moles of sodium hydroxide. And all of that comes from the concentration that was given to us in the original problem. So this is why it's critical to be very, very clear on what molarity means. Now our liters of solution cancel out and we have moles of sodium hydroxide. And keep in mind, previously we stated that titration relies on the fact that in order for a solution to be neutralized, we have to have equal amounts of acid and base. And if we look at our balanced chemical equation, notice that our ratios here are not 1-to-1. If there's no coefficient out front here, then this really means that the coefficient is 1. So for every 1 mole of acid, we need 2 moles of sodium hydroxide in order for the solution to be neutralized. And just like stoichiometry problems, we have to keep those ratios in mind when we are doing these calculations. We have to take that into account. So when we got to our moles of sodium hydroxide, we do have to account for these ratios. And we are saying that for every, I need a different color. Okay, for every 2 moles of sodium hydroxide, I need 1 mole of H2SO4. Okay, now our moles of sodium hydroxide cancel out and we get to the moles of H2SO4, which is exactly what we're looking for. So now it's really just a matter of plugging stuff in, making sure that we keep the correct number of sig figs. And keep in mind that these molar ratios are considered exact values, so they don't affect the number of sig figs in the problem. Okay, when I plug that in, I'm getting 0.00137 moles of sulfuric acid. And now that we have that gets plugged into our original equation because we needed to find the moles of H2SO4. We already had the volume of solution that was given to us in the problem. Okay, so we found it. It is here, and now we're going to plug that in. So there are 0.00137 moles of sulfuric acid. And we are going to divide that by 0.0200 liters of solution. And that'll give us the molarity. Okay, when I plug that in, I am getting 0.0683 molar sulfuric acid solution. Or alternatively, what you could do is express that in scientific notation. So that would be 6.83 times 10 to the negative 2. And both of these answers are correct. It just depends on what the problem is asking you to do.